Alright, well, in today's demonstration, I'll be covering two more studies, right? We'll be doing the time dependent study and the frequency domain study in COMSOL multiphysics. And the way we go about doing these two studies is we'll be utilizing this same micro cantilever structures, which I've been using in my previous demonstrations, right? Now, what we intend to do with these two studies is we want to do a transient sweep and a spectral sweep. Yeah. And I'll tell you why we're doing this in just a second. But what I want to help you understand here is the cantilever itself is going to be the same. We will have the same macro cantilever. We're going to add the constraints the same way, but only the force which we're applying here this time is going to be slightly different. You see, I have accommodated a variable for time here, which I did not do that in the previous experiments because we're trying to do a time dependent study, right? And time dependent study needs a parameter for time. So we have added that in the sign expression here. And we've added two variables called f0 and f external frequency. Now this is the frequency which we're giving, one external frequency, and the force we're delivering. So we need to add two variables and apply that as force. I will show how to do this. But before we do that, the rest of the cantilever is the same. So let us try making that. I go to model wizard. I select the 3D space once again. And for the physics itself is going to remain the same. It's always the solid mechanics for cantilever beams. I double click on that. Now the study, there's going to be a slight difference because you know how we want to do both the frequency domain and this time dependent study. Now let us start doing the time dependent study. We can do the frequency domain later on. I will add that as a study later on. Now when I just double click on the time dependent study, it's going to open the geometry window, right, which it always opens. I want to make sure that the length unit here is micrometers. Yeah. And the way to add the geometry itself, what do? You go to the geometry option. Under the primitives, I select the block option, which helps us model a cuboidal structure. And we apply the same dimensions which we have utilized in our previous experiments. It's 20, 220 and 2, right? And I build everything. And there's a cantilever structure. What's the first thing you do when you add a cantilever structure is that you add the material for it, right? I go to the materials option, I click on add materials, I double click on it, and we try to look for polysilicon since it's a macro cantilever structure. Polysilicon has a density of 2320, I think. 2320, and it has a Young's modulus of 169 gigapascals. You can remember them. You need to remember them for calculations later on. But once I've added the materials, I want to add constraints, right? And the way to do that is to go to physics here. Under boundaries, you select the fixed constraint, and you want to basically make one end of your cantilever fixed, yeah? And the other end of the cantilever is going to receive a boundary load. Now, I've told you before we write the expression for boundary load, I told you we need to add two variables, right? Now in console, the way you add variables is to go to the parameter option and global definitions, and I add two parameters called f0, which is going to be 1 micronewtons, and I'm going to add another parameter called f external frequency, which is going to be around 80 kilohertz. Okay, so it's going to be 80 kilohertz. So now I've added two variables. Now I want to write an expression with those two variables, and I make sure this is total force. Because if this is force per reference area, it's nothing but pressure, right? I don't want to give pressure, I want to give total force, and I want to give it in the negative z direction because I want to give it downwards, right? So I give an expression like that, minus f naught times, I write a sign expression with 2 times pi times f external, and I give an expression for time, which we need to do a sweep, right? After I'm done with the boundary load itself, I will now go to the mesh, and what we will try doing is we'll add the same structured mesh we've used so far, and I make sure that the size of this, you don't have to be too specific. I don't want to use a lot of computes. I'll go with, with extra fine. It should mostly be fine. And then we go to the study option here, right? And you see there's an option for range here, right? This range is very important. What you have to make sure is, see, you want to make sure now the range itself is the initial time, the final time, and the middle thing is the time step. You want to make sure that your time step is very small. I'll be giving 50 nanoseconds, okay? And you see there's an error. There's an error because it's saying the total number of elements are large. Because I'm sweeping from 0 to 1 second in 50 nanosecond steps, that's a lot of steps, right? And I'll tell you what this looks like. See, there is a solver, right? And your solver is going to basically go across the time domain. It's going to divide the time domain into time steps, right? And it's going to calculate a given displacement across all these time steps. But if your time step is really large, sometimes there can be discontinuity in how the graph is going. It can go very jagged, and your solver has a really hard time for solving all of this. But if you reduce the time step a lot, then your solver knows how exactly it should transition through different time periods, and it's able to go smoothly. It's not jagged anymore. But reducing the number of time step basically means it has to solve that many times more. So if your total time period is also large and your time step is also very large, this solver is not going to allow that, right? We don't, for transient analysis, need to go up to 1 second. I can go up to zero point 0.2 milliseconds and it will still be fine. Okay, that's zero point 0.2 milliseconds. So 0 to zero point 0.2 millisecond, and then I'm going in 50 nanoseconds time step. I don't have to include geometric nonlinearity because my force is very small. I can simply click on the compute option now, okay, and it's going to take like a minute or something. And you have to understand, I've not added damping so far. What do I mean by that? See, basically what we're doing with this experiment is there is a cantilever beam, okay? We are trying to oscillate this cantilever beam at a given frequency. Fine. Now, when you're trying to oscillate, it directly won't oscillate at that frequency. It's going to first transition between zero displacement, and it's going to have this period of time where it's not oscillating at the required frequency. This is the transient time, right? The amount of time it takes for the beam to start oscillating at the forced frequency. And the reason you see this time is because the beam will want to naturally oscillate at its own frequency. No, the resonant frequency around this beam I calculated was around 66 or 69 kilohertz. Okay. Now when it has these frequencies, it will try to displace more of those frequencies, and it will try to avoid reaching the force frequency initially. There's going to be some resistance, and usually you study this resistance to understand how good your damping systems are in any structural substance. Okay, there's going to be some damping systems you've established. You want to understand how good these damping systems are, and the way to do that is to basically transition your system between two steady states, from zero oscillation to steady state oscillation, and you try to see how much time it takes for this transition. If the time is very small, then your damping is really good. We'll be applying a Rayleigh damping. Right now, I've not applied any damping to show you how the beam is going to oscillate without any damping, right? Just to help you visualize how important damping is for any given system. It has finished computing now. We want to add a 2D plot, right? So I go to results there. I click on the 1D plot group, and this time I want to select a point graph, because if you're selecting for a line graph, it takes a lot of compute and it's not really required. So I just select one of the points and I make sure that the x-axis is in time, okay? And I simply click on plot. While it's plotting, look at the convergence graph. You see that your plot is not similar to this, the normal stationary study. It's not like it's not really going linearly or parabolic. It's going up and down, and this is expected of a time dependent plot because the values are constantly changing. What you have to look to make sure your solution is converging is it repeats. So this part here is repeating after a certain point, and if it's repeating in this fashion, you know that your solution is converging. So that's how you analyze it. Now I go to the point graph itself, and you see this has happened here because we are applying solid displacement. No, instead of solid displacement, let us only try to see the z-axis displacement, and to do that is to search for something called w, right? You see this is z field displacement. I only want to plot the z field displacement, and it looks something like this. You see it's not reaching a steady state, because if it was reaching a steady state, it would have looked like this. It will oscillate and it will reach this part here. But this graph is not really reaching a steady state, is it? Because I've not added any damping. So you see, without damping, the system is not going to reach steady state soon. It's going to reach at some point, but it's not happening very soon. But now I'll add a damping. I'll right click on the linear elastic materials section here, and I'll click on the damping button. We want to add something called Rayleigh damping. Now every system will have its own values for mass damping and stiffness damping. I've already calculated this for this block. You can use this damping setup. Now, your mass damping is going to add a lower frequencies, higher frequencies, stiffness damping is going to damp your system. If you apply these damping, and then I'm going to like what compute again. The way to do that is go to studies here and click on compute again. Yeah, it's going to take a moment there, but look at this screen here. Now, when I do that, it's going to oscillate, yes, like the previous experiment itself. But after that, it's going to reach a steady state. This tells us that your damping has efficiently reduced the transient time, which is the goal of your experiment. The goal of your experiment is to tell the amount of transient time it has taken for your system to transition between two steady states. That is all, right? That is everything for what do you say, time dependent study. The next study we'll do is spectral sweep. The logic behind it is the same. You know how at resonant frequency, which is around 60 some kilohertz, right? The displacement is going to be the maximum. So we basically try to measure for the displacement, and we'll see at what point of frequency the displacement is going to be maximum. That point of frequency is our resonant frequency. So we're only checking for the first rigid body mode, the first mode. You know, in eigen frequencies, you have around 5 or 6 modes. You don't need all those modes. You only need the first resonant frequency. And we'll use the same equation we have utilized in our previous instances. You know, I think I've showed you this expression, right? The Euler Bernoulli's cantilever beam expression. Yeah, this expression. We'll use the same expression to verify the spectral sweep. But for now, I'm just still waiting for this to compute. It's still computing. But yeah, we'll be utilizing the same expression. You can use the same expression to calculate it yourself, but this time you have to remember the modal constant you're utilizing is only this, by the way, okay? You'll only be utilizing you'll be only utilizing this because we only want the first resonant frequency, and you have to calculate this for your own for this setup. What your breadth was around 20, your height was around 2 micrometers. You have to calculate for the moment of inertia. Your Young's modulus this time, what is a Young's modulus? It's 169 gigapascals. So you have to calculate that, and the area you'll have to change. You'll have to change also the density, which is 2320 this time. Apply all of this, and I think you'll get your values around 66 something kilohertz. Okay, we will verify this in simulation, but you also have to verify this in writing and in theory. You have to use this equation and verify that. Okay, we'll check if it has finished solving. It has finished solving. Now look at the point graph again. You notice that all of a sudden, see, it has reached a steady state, right? This was not the case without damping. And how much time it has taken? If you add the graph markers here, you see it has taken me approximately what, around this point, if you see, around point 0.5 or 0.05 milliseconds. It's zero point 0.5 times 10 to the power negative 4. So it's basically 0.05 milliseconds. At this point, it has reached steady state where it is oscillating the same way. And your convergence plot is also, you see the same thing is repeating. The same segment in the time step is repeating. This tells that it's reaching convergence. And you can make note of these values. These are important. These are maximum displacements present in the transient time. The only thing you have to write down is it's going to take zero point 0.05 milliseconds to reach transient time with the damping. Without damping, we couldn't ascertain it, but it took a lot of time. It's going to take a lot of time to finish damping, but with this setup, it has taken zero point 0.05 milliseconds. So this is the plot and the goal of this experiment. Now we'll go for the next part of this same experiment. We will add a study, and the way to add a study for the frequency domain is you go to the study option here, click on add study twice, and you see there's an option for frequency domain. You double click on that, and if you see in this screen, there's a frequency domain study that has been added now. Before I do the study, I have to make sure now that the boundary load does not have an external frequency, because we are driving the frequency through the frequency domain study, right? So I just want the force. The external frequency is going to be driven by the study itself. So I have to make sure to change this to force. And now if I go to the frequency domain, now we have to sweep, right? The way to sweep, how do you sweep? You basically write the equation range, and you want to sweep from, since I know it's not going to resonate anywhere near 0 or whatever, I can start from 10 kilohertz only. Okay, and I'm going to sweep in 1 kilohertz steps. Okay, That's the resolution. I think 1 kilohertz is okay. You don't have to worry too much. We can go all the way to 100 kilohertz because experiment, like theoretically, I found out the resonant is around 66, right? So if I'm going to sweep this much, I'm definitely going to identify the resonant frequency. I can simply click on compute now, and it's going to give me a value. It's going to take some amount of time. Like I think it's going to take around 30 seconds or 40 seconds, but we'll give it time. This time also we'll be using point graph, okay? You don't really always have to use line graph. You can use line graph for all the cantilever beam experiments we have done beforehand. But for this one, you don't need to because it takes a lot of compute. So we can go to results and we can add a 1D plot group again where we'll select the point graph once again, okay? I'll select the same point. You can select any of these points. I'll select this point. And you have to make sure that this time it's selected to study 2, the frequency domain part, all right? And we don't want solid displacement, no? Like last time, let us use W itself. Now I'm going to plot it, but if you, and make sure the x-axis is parameter value, but if you notice, if I just plot for this directly, you'll see this negative displacement also, and this is confusing. You don't want negative displacement. So I'll make sure that this is absolute. Okay, so it kind of calculates the displacement as a whole. I don't want to know if it's down or up, right? When I plot this, now the graph looks clean. I know it's going to displace the most at a certain point, right? To calculate that, I can delete this. I don't know what that is, but sure. Now to calculate that point, you can right click on this and add a graph marker again, and you see that point is around 66 kilohertz, right? It's exactly what we calculated. So by this means, we are able to find the resonant frequency of our given cantilever beam. This is the first rigid body mode. You don't have to calculate for the other modes, but for a spectral sweep or frequency domain, you can only calculate for the first mode. So this is the end of our experiment. I hope you could follow along. If you have doubts, you can let me know in the comment section. And for the next experiment, we'll be doing parallel plate capacitors. Okay, for a change, we'll be doing parallel plate capacitor, and we'll be doing electrostatic study. Yeah, so it's a little different. It's going to be a little more fun. But this is the end of all the cantilever beams experiment. I hope you're having a good day. You take care. Bye bye.